Hello dear students, in this video we will discuss about indeterminacy. Before going to start our topic indeterminacy, I would like to tell you what is statically determinate structures and what is statically indeterminate structures. So here you can see a structure is said to be determinate if conditions of static equilibrium are sufficient to analyze the structure. So we know that in determinate structures, our bending moment and our shear force are independent of properties of material and cross-sectional area. And we also know that in statically determinate structures, no stresses are induced due to temperature changes, and also no stresses are induced due to lack of fit and support settlement. So let's discuss statically indeterminate structures. So, statically indeterminate structures are those in which, if conditions of static equilibrium are not sufficient to analyze the structure, then we need to analyze these structures based on additional compatibility conditions which is to be required to solve the structure. So we know in indeterminate structures, bending moment and shear force are not depend upon the properties of materials and also not depend upon the cross-sectional area. And also the stresses induced due to temperature variation occurs in statically indeterminate structures. Also, stresses are induced due to lack of fit and support settlement. So now let's discuss the degree of indeterminacy. So degree of indeterminacy, we have static indeterminacy and kinematic indeterminacy. So further, static indeterminacy, which can be classified as external indeterminacy and internal indeterminacy, and kinematic indeterminacy is further. So here would start with static indeterminacy. So those structures which cannot be analyzed using equations of static equilibrium alone are called as indeterminate structures, or we can say these are your hyperstatic structures. Okay, so to analyze these structures we required extra equations, and these equations are called as compatibility equations, we know. Okay, so here first discuss about the external static indeterminacy. It is denoted as DSE. Okay, so it is related to the support system of the structure, and this external static indeterminacy is equal to the number of independent external reactions in excess to available equilibrium condition for a static equilibrium. Okay, mathematically it is say that DSE is equal to RE minus R. Okay, so what is this RE? RE is the total number of independent support reactions we have. So these are the total number of independent support reactions. Okay, so here we have that if we are having a fixed support, then RE value is 3 for fixed support. Then again we have if we have a hinge support, then we have RE value is 2, and for roller support RE value is 1. Okay, so these are the total number of independent support reaction, that is RE. And what is R? R is the total number of available equations of static equilibrium. Okay, so these are the total number of available equations of static equilibrium. So it is for 3D structures we have R is equal to 6. Okay, and for 2D structures we have R is equal to 3. Okay, so you have to keep in mind for 3D it is R is equal to 6 available equations, and for 2D structure R is equal to 3. Okay, we will see in this in example. Okay, so first let's take one case, that is case 1. So case 1 is 2D beam subjected to general loading. Okay, so here you can see this figure 1, that this is your fixed support. Again this is your fixed support, this is a fixed beam. Okay, and here the loading is general, so this is not having a vertical load. Here this is your inclined load somewhere midpoint in the beam, and this fixed support we know three reactions are acting here. So one is horizontal, another is vertical, then third one is your moment here. similarly here one is horizontal, then vertical, and this is our movement here. So we have to find our external static indeterminacy. So we know here Re is equal to 6. That is your Re is your 1 this reaction, 2 is vertical reaction, 3 is your movement, then 4, 5 vertical here again, and movement 6. So Re is equal to 6. Okay, since it is a 2D structure, so R is equal to 3. We have our available equations of static equilibrium is 3. This is R value is 3 for 2D. So here R is equal to 3 and Re is 6. That is your total number of independent support reactions. So these are the total number of independent support reaction. That is 1, 2, 3, 4 here, 5 here, and 6 here. So R is equal to 6 and R is equal to 3. So to calculate our external static indeterminacy, that is DSE, Re minus R is the formula. So Re is equal to 6, R is your 3, that is equal to 3. So for general loading system, a fixed beam is statically indeterminate to third degree. Okay. So this is your fixed beam and it is indeterminate to third degree. Okay. As your DSE value is 3. Okay. So let's take case 2 here. So for case 2 again for 2D beam with vertical loading. Okay. So this is your fixed support again or fixed support again, and this is your fixed beam figure 2 here, and we are having a vertical loading. So if we are having a vertical loading, then your axial load is neglected. Okay, so here we can't consider our axial loads here. Okay, so here we have our available equations are only 2 for this fixed support and similarly for 2 for this fixed support. We not consider your horizontal reaction here as fifth reaction and sixth reaction again in horizontal reaction. So you have to keep in mind that if you are having a vertical loading on your 2D structure or 2D beam, then we have to consider your two available equations we have on each fixed support. So here your Re value is 4. Okay, so Re value is 4. How it is? One is vertical reaction, another is your moment 2, third is your again vertical reaction for this support, fourth is your again movement for this support. Okay, and fifth, that is your horizontal is not considered here because we are having a vertical loading. Okay, so we neglected your horizontal loads or horizontal reaction here. Okay, so here also our sixth reaction, that is horizontal reaction, is neglected. So we have our static equilibrium equations 2 here, 2 here. Okay, so 4 static equilibrium equations, or Re value is 4 here, and static equilibrium available equations we have 2. Okay, so our horizontal third one is horizontal, we are not considering here. That is, this is one is your vertical reaction and another is your moment. Okay, so R is equal to 2 here. So Re is 4, R is 2, so DSE is equal to Re minus R. So then we have Re is 4 minus 2, that is 2. So here beam indeterminate to second degree. Okay, so this is your fixed beam again, and this is indeterminate to second degree. Okay, so for vertical loading. So keep in mind. Okay, so hence for general loading, the external indeterminacy is given by, that is DSE is equal to Re minus 3 for 2D structures and DSE is equal to Re minus 6 for 3D equations, 3D structures. Okay, so let's quickly solve your examples on external static indeterminacy. Okay, so this is your beam here. This is a 2D beam with a fixed support at A joint and with a beam with hinged support at B. Okay, so determine your degree of external static indeterminacy, that is DSE. You have to find the value of DSE. So we know DSE is equal to Re minus R. So Re is your number of independent equations. So here we have our three equations. Okay, suffix support is having three equations because we are not giving any loading here. So we are considering here your general loading condition. Okay, so for general loading here, DSE is equal to Re minus 3. So Re is equal to 5. How it is 5? At fixed support, we know the one vertical reaction, one horizontal reaction, and one moment exist. Okay, so three equations at fixed support here, and for hinge support we know two reactions are acting. So one is vertical and another is or horizontal. So here you consider 1, 2, 3, 4, 5. So Re value is 5 here. For general loading, Re minus 3. 3 is your three static equilibrium conditions equations. So that is one is your horizontal, vertical, and your movement. So Re is 5 minus 3 is 2. So DSE is equal to 2 for this general loading of so given beam is externally indeterminate to second degree. Okay, so by this way you can calculate your external static indeterminacy. Okay, simply you can learn the formula Re minus available static equilibrium equations. Okay, so now move on to the next example based on your static external indeterminacy. That is, this is your space frame. Okay, so this is your figure 4. You can refer this figure 4, and you can see here that this is a space frame and we have to determine the value of external static indeterminacy, that is DSE. Okay, so what we have to see here, that this is your fixed support here. Okay, this is your fixed support, this is your roller support, this is again your hinge support, pinned support. You can say hinge or pin are same thing. So this is a hinge support here, and this is your fixed support here again. Okay, so we know for fixed support, and this, since this is a space frame, so for space frame we know at fixed support we are having Re value is 6. Okay, so here you can remember that for space frame your fixed support is having 6 equations. Okay, so for roller support it is 1 only. Okay, again for your fixed support it is 6. Okay, and again for your hinge support the Re value is 3. Okay, that is your Rx, Ry, or Rz. Okay, so three reactions, that is in x direction, y direction, or z direction. So at hinge support of 3D space frame, we are having hinge support, we are having three reactions here. For your roller support, we are having only one reaction here. For your fixed support, we are having six reactions. Okay, so keep in mind for space frame for 3D structure, we are having fixed support as 6. Here, roller support as 1 or hinge support as 3. Okay, so after calculating these values, we are having total Re value is Re1 plus Re2 plus Re3 plus Re4. That is 6 plus 1 plus 6 plus 3. So total Re value is 16 here. So for general loading, we are having a formula, that is to calculate DSE is equal to Re minus 6. So Re value we are having 16 and 6, that is your equations, that is static equilibrium equations for 3D frame, that is 6 here. So 16 minus 6 is 10. So since all the reactions are non-parallel here and non-concurrent. Okay, so since all the reactions are non-parallel and non-concurrent, so here given frame is stable. So that's why this frame is stable and indeterminate to 10th degree. Okay, because we are having DSE value is 10. Okay, so how to calculate DSE? We are having a formula, DSE is equal to Re minus 6. Re is the number of reactions acting at the support, and 6 is the total number of equilibrium equations for 3D space frame. Okay, so here you can refer this example again. Okay, so this is how we calculate our external static indeterminacy. Okay, now let's move on to internal static indeterminacy, that is denoted as DSI. Okay, so it is referred as DSI. Okay, so if we are considering here or case 1, that is for pin jointed plane frame 2D truss. Okay, so we are considering a pin jointed plane frame 2D truss. As we all know that in trusses all joints are hinged and loading is applied at joint only. Okay, so the self weight of members are neglected here, and hence all the members of truss will carry only axial force, either it is compressive or either it is tensile. Okay, so if we are considering a truss, and in the truss we are having m number of members in the truss. So if I am considering truss, and in the truss we are having m members. Okay, then there will be m internal member force, axial force in each member. Okay, so at each joint in the truss we are having two equilibrium conditions, that is summation of fx is equal to 0 and summation of fy is equal to 0. Okay, so let there are j number of joints, we are having a j number of joints. Okay, so hence to total equilibrium conditions available on all joints will be 2j. Okay, so if we are having a j number of joints, then we are having a total number of equilibrium equilibrium conditions will be 2j. Okay, so out of these 2j equilibrium conditions, or three conditions or three equations are used to determine external support reactions. So hence your net equations to determine internal reaction will be 2j minus 3. Okay, so we are have to focus here, that is your net available equations to determine your internal reaction will be 2j minus 3 here. Okay, so to calculate your internal static indeterminacy, we are having a formula, that is total number of internal reactions minus available equations of equilibrium. Okay, so that is dsi is equal to, that is m minus available equations of equilibrium is 2j minus 3. Okay, so this is a 2j minus 3 here. So we are having a formula. So for pin jointed plane frame or 2D truss, dsi is equal to m minus 2j minus 3 is the formula. Okay, so you have to keep this formula. Okay, so if DSI is equal to 0, if I am having a DSI value is 0, then our truss is internally determinate. Such truss are called as perfect truss. Okay, so this is usually asked in your examinations, that write the example of perfect truss. So you have to write your perfect truss as if your DSI value is 0. Okay, so truss is internally determinate. If you are having a DSI value greater than 0, then the truss is indeterminate here and over stiff. If your value DSI value is greater than 0, then it is over stiff and indeterminate. Okay, so and if your DSI value is less than 0, then it is internally deficient and geometrically unstable. Okay, so here you have to keep these three conditions in mind, that is DSI is equal to 0, DSI is greater than 0, then truss is indeterminate and oval stiff, and DSI is less than 0, that is internally deficient truss and geometrically unstable truss. Okay, so this is our internal static indeterminacy as case 1, that is your pin jointed plane frame here. Okay, so in our next video we will cover our case 2 as 3D truss, pin jointed space frame truss, and we will consider our 2D and 3D rigid frames also. Okay, and we will solve all the questions which is usually asked in your examinations related to indeterminacy. Okay, so we will solve each too many number of questions here. Okay, so this is, thank you so much, and we will meet you again. So thank you so much.